Okay, in this video, we're going to look at a new uh, idea. We're going to look at the Gibbs Free Energy Change, which is usually given the symbol delta G. Okay, and here I've written it. So quite often we're using this. We're going to have to calculate the Gibbs Free Energy Change for reactions. It changes according to the temperature, and so we're dealing with understanding conditions 298 Kelvin. So everything's there. Yeah, 298 Kelvin. Okay, but right, let's just let's concentrate on this expression here. Right, let's just have a little think about it. So what are the units of delta H? Well, we usually measure delta H in kilojoules per mole. Delta S, well, we usually measure that in, if your values are usually quoted in joules per mole per Kelvin. So in order to make it compatible with this, well, we need to change that, and we need to turn it into, we need to convert it into kilojoules per mole. And it's important that you don't forget to do that, otherwise obviously you're going to get completely the wrong answer. Because usually, a typical value of delta S for a reaction might be something like 200 joules per mole per Kelvin, sorry. Okay, whereas if you look at delta H, well, the typical value for that might be like minus 300 kilojoules. Okay, so we do need to convert our delta S's, so that would be equal to obviously 0.2 kilojoules per mole per Kelvin. Right, so that's important to convert that into that. Right, so I just rub this out now. So that's in, and what do we measure T in? Well, T is absolute temperature, so we measure that in kelvins. So what are going to be the units of this bit of the expression? Well, it's going to be kelvins times kelvins to the -1. So they're going to disappear, aren't they? So the units are going to be kilojoules per mole for that bit, for minus T delta S. So that means the units of delta G, they are always going to be in kilojoules per mole, because the units of delta H and the units of this are kilojoules per mole. So delta G measured in kilojoules per mole. Right, what is what is delta G? Well, it's called the free energy change, and it can be used for a number of things. But what we're interested in doing it, it tells us, delta G tells us what delta S total for a reaction is. So in other words, delta S of the reaction and of the surroundings. Okay. Right. So so delta G then, if I'll put down here in this column delta S total. In this column I'll put delta G. Right. If delta S total is positive, then delta G is negative. If delta S total is 0, then delta G is 0. And if delta S total is negative, then delta G is positive. So what that means is, it's a quick way of using the second law of thermodynamics. So the second law, the way we're going to use that is delta G for any change must be greater than or equal to 0. Okay, if it's not, the reaction is impossible. It will break the second law, and so it's not going to happen. So that's what we're going to use delta G for. Now, just be a little bit. I'm going to write down here some that tells about the reaction. Okay, so here's the reaction. If delta G is negative, okay, it's possible. And if its delta G is positive, it's not possible. If it's 0, then it means that the reaction Well, it can go backwards and forwards. So what kind of a reaction is that going to be? It's going to be an equilibrium reaction. Unfortunately, there's quite a confusing word used here sometimes. Okay, and this is the word spontaneous, and it's used in some books. Okay, a bit too thick. 1 minute. Spontaneous. Right, spontaneous in everyday life means it just happens by itself, doesn't it? It doesn't in chemistry. It means the reaction is possible. That's what it means. It doesn't mean anything else. I.e., it means that delta G is greater than, sorry, is less than or equal to 0. So don't confuse the meaning of spontaneous as the sort of everyday meaning. It's different. Okay, so let's have a go at calculating delta G for a reaction. Let's have a look at the formation of magnesium oxide from magnesium and oxygen. Okay. So we've got magnesium solid plus a half O2 goes to MgO solid. And let's see if this reaction can occur. Is this possible? We all know it is possible because you can burn magnesium ribbon, can't you? We're going to see if it's possible at 298 Kelvin. So we have delta H for this reaction. Well, we don't really have to work this out because what we're doing, this is actually equal to delta HF of magnesium oxide, because what we're doing, we're forming 1 mole of magnesium oxide, aren't we? So delta HF of that is minus 602 kilojoules per mole. And in the previous video, we worked out that the delta S for this reaction was equal to minus 108.3, careful, joules per mole per Kelvin. Okay, so we want to work out delta G for this reaction to see if it's possible. And remember what we said about delta S? Look, this is negative, so we said, does that break the second law? Because look, the entropy is going down, but it's not the entropy total, it's the entropy of the system, of the reaction, isn't it? That's going down. The entropy of the surroundings of the universe goes up. Why does it go up? Because delta H is negative, so it makes it all hotter, so it increases the entropy that way. Anyway, let's work out delta G. So delta G is equal to delta H minus T delta S. We're going to be doing this reaction at, say, room temperature, which is 298 Kelvin. Right, let's do that then. So delta G is equal to minus 602 multiplied by, minus 298 temperature, and we need to convert this value into kilojoules per mole per Kelvin, don't we? So that's minus 0.1083. Okay, so that is equal to minus 602. And this bit is 298 is 32. So that becomes a plus 32.3. So delta G is going to be 569.7 minus 569.7, and the units are kilojoules per mole. And so therefore we can say the reaction can happen at 298 Kelvin, as we knew in the first place, because we know you can burn magnesium ribbon. But let's say, look, it can happen. Does it mean it will happen? No, it doesn't. It tells us nothing about the rate of reaction. If you get a piece of magnesium and you don't light it, it won't burn, will it? It'll just stay as magnesium. So delta G tells us nothing about the rate, okay? Delta G tells us nothing about the rate of reaction. Rather like equilibrium constants, yeah, it tells you which way the equilibrium is, where it's favor of the products of the reactants. It won't tell you anything about the rate of reaction, and it shouldn't come as any surprise to you that delta G and the equilibrium constant are mathematically related to each other. We don't need to know about that for the A-level spec, but they are related. And really, looking at delta G, looking at Kc, you're really just looking at two different sides of the same coin, really. Okay. So there's a quick example of how to work out delta G for a reaction and how it will tell you if the reaction is impossible or not possible.